Stanford University.
Okay, welcome to Lecture 2 of Stanford CS193P, spring of 2021. So in Lecture 1, we started off on our quest to build a card game here with just little text, hello world. And we learned how to modify it, change its color, put padding around it, and then how to combine it with another thing, this rounded rectangle, using a Z-stack. Now we're going to take an even bigger jump, which is we're going to make multiple of these cards. Making multiple cards, we're not going to quite jump all the way to having a whole grid of them here. We're going to start by just making a single row of them. It's actually quite easy. We just need another view combiner. This view combiner is called an H-stack. So that's horizontal stack. We're stacking them horizontally. And I'm going to take this Z-stack that we built right here, and I'm just going to put 4 of them in here. All I used was an H-stack to combine these Z-stacks. This code is kind of gross, though. If you really had to program this way, imagine we have 20 cards. We're going to have 20 of these Z-stacks with around. No, I mean, clearly we're not going to do it this way. And why? Because, you know, for example, this still says hello world. We want these to be emoji in here. So we're going to edit each one of these to be something? No, we're not going to do that. Makes no sense. So how are we going to clean this code up dramatically to make it make a lot more sense, both to a reader and to make our code really manageable? Well, what we're going to do is create a dining room chair Lego. Remember I told you that we can create Lego out of other Legos. We kind of did that with a Z-stack here. We created one card Lego, kind of a dining room chair Lego. We kind of did it on the fly. There's no reason we can't create a new struct that behaves like a view, which is a card view, a dining room chair view, if you want to think of it in the Lego terms. We can do that anytime we want. And in fact, we're going to do that all the time because in SwiftUI, we really want our views to be quite small. We want them to have very little code in them. It's better to have more smaller views than fewer larger views. A view with this many lines of code is pretty rare. And this, we're only just getting started here because imagine how complicated our card UI is over here. And yet I'm telling you that even this many lines of code is a lot in a view. Okay, lots of small views. That is the design paradigm of SwiftUI. So we're just going to take this little Z-stack of the rounded rectangle and the text and make our own new struct that behaves like a view. I'm going to call it card view. I'm literally just going to go down here and type it in. It's a struct. It's called card view. It behaves like a view. That means it has to have a var body, which is some view. I'm going to set the value of it by throwing a function right there. It's going to have to return something. It's going to return this Z-stack right here. So I'm going to copy and paste that right there. Of course, we don't need the return statement right there. And voila, I've now created my dining room chair view, which is my card view right here. And I can use that up in here in the same way that I would use any other view, any other Lego, like text or rounded rectangle. I can just replace all of these by just putting a card view here. Okay, and we know that open parentheses is closed parentheses. That's how we create something. So I put 4 of those in there. Now if I resume, I get the exact same result as when I had all those Z-stacks in there. And look how simple all this code has become. Much more understandable, much simpler to type in, and much more powerful all at the same time. Okay, this, what you see right here, this is the heart of doing SwiftUI programming, is defining these dining room chairs and then stacking them together and modifying views as you need them along the way. Let's go ahead and make our things look a little more like cards by getting rid of hello world and putting an emoji there. Pretty much all Mac apps in their edit menu, and Xcode has got the same thing, have this emoji and symbols. You can also do Control Command Space to bring that up. We're going to do the same thing that we did over here and have travel ones. Okay, see our little travel emoji right there. So I'm gonna go back here and we'll start with airplane. So I've just put an airplane in there. And that worked great. It's kind of a small little airplane. You know, these are huge cars, small airplane. So I'd like to make this a little larger. Again, at any time, even after I've done this factoring, whatever, I can always click on this text, go over to the inspector. For example, its font can be set. You see, font inherited. I'm going to switch it to large title. I believe that's the largest built-in font that there is, and that made it larger. Now, it's still not quite as large as these ones are over here. They're still kind of small, and we're going to learn next week a little bit how to make the fonts even larger and also to make the fonts kind of more fit the size of the card they're on. So this is a smaller font, and this flags, for example, is a much larger font. So we'll learn all about that next week, but for now we're going to use this built-in font that we have here, large title. It makes it look a little bit better. Now, we're pretty proud of ourselves having gotten this far building our card game, but it actually has kind of a fatal flaw that's a little bit hard to see. And the reason it's hard to see is we've been doing this whole thing with our preview window in what's called light mode. So in iOS 13, they introduced this concept of having your phone in dark mode or light mode. So in dark mode, the background is black, pixels are basically off as much as possible, and your UI is light colored in contrast to the black background. And these cards look fine. They look just like what we see over here. And you'd think, oh yeah, we did a good job. They're kind of tall and skinny, but they at least look like cards. But they don't look very good in dark mode. And it's a great opportunity for me to show you how we can adjust this preview, because we've just accepted what this preview has chosen to show us. For example, this happens to look like an iPhone 12 mini because we ran that in the simulator, so it chose that for us. Maybe when you run it, if you don't choose iPhone 12 mini, it'd be something different. Well, I want to be able to control what kind of phone I see right here. And maybe I even want to have different kinds of them looking here at the same time as I change things. Here's how we customize this preview. And I'm not going to go into the great detail, but I'm going to give you the general concept. And just like with all of these things, you're going to learn more about it as the quarter goes by. So this preview is controlled with this code that we moved out of the way. It's this code down here that controls how your preview looks. And right now, don't worry too much about these 2 lines of code here, but you can see it's just displaying our content view. But if we click on this content view, oh, it has an inspector as well. We can, for example, choose a device. And we can also pick the color scheme here. And when I pick dark mode, it puts this into dark mode, and you can see our cards don't look so good in dark mode. And it added this line of code right here. This is a view modifier that's modifying our content view. Remember, our content view is just a struct that behaves like a view, so it can have these, whatever the view modifiers, padding, etc. So this is just like padding. It's a view modifier that says, hey, when you display this thing, please prefer this color scheme dark. So now I see dark. But what if I want to see it in dark and light? I want 2 simulators in here. No problem. We can actually copy and paste this and have the second one, instead of dark, be light. So now I have both a light and a dark little preview at the same time. And just scroll back and forth between them. Inside here, we can kind of put however many views we want. This is essentially a bag of Lego view builder thing here. And we just list as many as we want, and it'll make a simulator for each one that it encounters. What's wrong with our cards here? Well, they really want to have this white background even in dark mode. Cards, it doesn't really make sense for the card to essentially be transparent where we can see through. We want this filled in white. How are we going to fill this thing in white? Well, unfortunately, rounded rectangle, there's no way to have one be stroked and have this red border and then also filled. So having dot fill here actually would mean something slightly different. When we said stroke, that actually took our rounded rectangle, kind of made a racetrack around the edge of it, and that racetrack is only 3 points wide, but it could be even wider. And so when we say dot fill right after a dot stroke, we're actually talking about filling the racetrack that we made around the edge. And in Swift, you can fill with other things beside colors. You can fill gradients and patterns and things like that. So you could see how fill could be useful for filling what's actually in that racetrack. But here what we want is to fill the inside part, the part inside the stroke, not the racetrack itself, but what's inside the racetrack, the middle of the rounded rectangle. We can't do that with a single rectangle. There's just no way to both create the racetrack around it and fill the middle of it. So we're going to need two rounded rectangles actually. So I'm going to copy and paste this, and I'm going to create one rounded rectangle that's filled, and then on this Z-stack, remember, Z-stack stacks them on top of each other. So I've got a filled rounded rectangle, and then I put the stroked one on top of it. Of course, I want the filled round rectangle not to be filled with red. I want it to be filled with white. So I'm going to say down here, dot foreground color dot white. And that's going to fill our rounded rectangle with white in the background there, and then put the red on top of it. And it looks good in both dark mode and light mode. That was a little bit of an excursion, mostly to talk about preview, kind of a good example of showing why I would want to go down to my previews and create other previews. And we'll learn as quarter goes by that there are other view modifiers that you can do that make them appear differently when they're being previewed. All right, so that's enough of that. We've got our nice cards here. We've got multiple cards, that's good. What about face up and face down? All of our cards here are face up, but in our UI over here, these cards are face down. And if I touch them, oh, they go face up. So face up, face down. How do I make my card appear face down? And then how do I make it so when I tap on it, it'll switch between face up and face down? Okay, both of these things, pretty straightforward. Let's go over and talk about face down. Here's our code that looks face up. I don't know if you remember when I first talked about these Lego bags, right? The bags of Lego things that we're passing as the content argument here to the Z-stack view combiner. But I said it could have ifs. I can put an if in here that says if is face up, which I just made that up, by the way. This is face up. We'll have to do something to make that exist. Then I'm going to do this. But if it's not face up, then I'm going to just have a filled rounded rectangle, because that's what our face down cards look like. This face up is, I just pulled it out of my hat, so it's not really something. That's why it says it cannot find is face up in scope. But all I need to do to have something like is face up that controls how I look is just add another variable. So I'm going to say var is face up is of type bool. So it is a Boolean. And that's going to get rid of this error because I've got this Boolean and I'm just checking this Boolean in my struct. Couldn't be simpler. Uh-oh, though, got some errors up here. Why did fixing this is face up thing here cause errors up here where I'm creating my card views? Well, this is actually happening because of a very important rule in Swift, the Swift language. So let this sink in, this rule. You cannot have variables that have no value. Variables always must have a value. From the time they're created all the way for their entire lifetime, they must have a value. There's no such thing as a variable with no value in Swift. Now, there is a kind of variable called an optional, which we'll talk about next week, that looks like it's no value, but it's not that it's no value, it just has the value not set yet. It's a little bit different, but a Boolean has to either be true or false at all times. This up here, I'm going to explain why this error is happening up here in a moment, but let's talk about how this thing can get a value. This is just a variable, so we could do the same thing we do here. Let's just put a little function here and have it return false. Is face up. The value of this variable is now going to be calculated by executing this function. This function returns false. So when we go back here and try again to build. And by the way, when you make a change that won't compile, sometimes your preview will say, I can't do this. It doesn't work. And so when you try again, it doesn't always work the first time. Sometimes it takes a couple of try agains. But it does work. Look at that. All of our cards are face down. Is face up, returns false. They're all face down. And if I change this to be true, then all of our cards are face up. So that's one way to do it, but we would probably not use a function here when we can do something much simpler, which is equals true. When we say equals true, we are giving this variable an initial value. And it's currently with the way our code is, it keeps that value forever. So these cards are always face up, or I can say false and now resume, and they're all going to be face down. So that's one way to do it. But what if I don't provide a value here? I don't do the little function way and I don't do equal something. Then what happens? Then I get these errors up here. And what this is saying is missing argument for parameter is face up in call to create this. If you have a variable in one of your views and it's not given any initial value, then you have to provide that value when you create the view. And we do that by saying is face up, true, for example. Notice that eliminated that error for this line. It's completely gone because we are now initializing this variable. This hopefully to you looks very similar to this, right? When I was creating a rounded rectangle, I had to provide this argument corner radius. This is not the only way to make this work, so I'm not sure if corner radius really is a var inside the rounded rectangle view. Might be though. But if it were, this is exactly the same kind of syntax that you're going to get as we get up here. So we can do this for all our cards, give them all a face up, and we maybe have them be different. Let's have maybe these two middle ones be face down, and the two side ones be face up. We resume, and then, sure enough, it's working perfectly. This is an important thing to understand about these variables. They have to have values, and if you don't set them inside of your own view, then whoever creates them is going to be forced to do it. Oh, by the way, if you define this to be, for example, true, then this is going to override that. The person who's creating it wins if you've got both a default value and you specify a value here. So notice that these two guys who say that it's false, they're still winning. Those are face down, even though the default is true. But it does allow us to remove this. You can remove this, perfectly legal now because there's a default value. And if we remove it from these two, then we're going to have them all be face up. Okay, so before we move on with our card here, I want to take a little time out here to show you something else we can do with a bag of Legos view down here. When we added this is face up var, kind of copied and pasted a little bit of code right here to make the back of the card, right? We had this, we copied and pasted it, and I'm just starting to notice that that copying and pasting is resulting in my having this same little expression multiple times in here. And of course, in programming, we don't want to do that. We want to be able to use local variables, for example, to store things like that. So a bag of Legos view, in addition to having a list of views, obviously, and these if-thens, can also have local variables. I'm going to create a local variable here. I'm going to call it shape, which is going to be the shape of my card right here. Shape equals, and I'm just going to put my little rounded rectangle here. And now that I have this local variable, I can replace all the times that I use this with shape. Shape here, shape here, shape here. And since this has made this such a small little word in my line of code, I probably would even put these on the same line right here. I could do the same thing with my text. So I've got a double benefit here of not repeating typing this over and over and making my code a little tighter, a little easier to read, a little easier to understand that there are three things that are Z stacked together here to make that work. You notice that doing this introduced this little warning here, this yellow warning. And so we always want to fix our warnings. You know, the red errors we have to fix, but the yellow warnings, really we have to fix those too. Our program might function, but if warning sometimes is an indication something not going so right. Let's take a look at this one. It says variable shape, that's this thing I just introduced, was never mutated. It says consider changing it to a let constant. So it's saying call this let instead of var. So I'm going to do that. Instead of var, then I'm going to type let, and that means let this shape equal that, and no more warning. So what is the difference between var and let? Well, var is short for variable. That means that's something that's going to vary, something that's going to change. And clearly our rounded rectangle is going to always be our rounded rectangle here. It's not going to change. So that makes this really a constant. So we always want to use let when we're defining variables that are not really variable, they're constant, and use var when they're variables. Now this is a var because it's changing every time someone asks for it because it's executing this function to find the value. So lets are just constants that we set things to. Now, one thing that's interesting about this line of code here, kind of different from this variable up here, is that there's no type. Right up here we have the type Boolean. Here we have a type also, some view. There's no type in here. And of course the type of this is rounded rectangle. And we didn't have to type this. Swift again doesn't like us to have to type the same thing over and over. So it says, no problem, I will figure this out for you. If you just leave this off, I will figure it out for you. And that's, again, not only good for less typing, but what if we decided, we left that in there and we decided, no, I want my cards actually to be circles. I'm going to type a different kind of shape in here, a circle. Well, of course, that's going to generate an error because a circle is not of type rounded rectangle. But if I had left that off, then when I changed this to a circle, it would all just work. See, look, those things changed to be circles instead of rounded rectangles, and this shape automatically changed to be the right type. We let Swift infer the type. You're going to hear me use the word infer when I'm talking about types a lot in this course. And inferring a type just means the Swift is going to look at the context that this thing is in, and if it can, and most of the time it can, it'll put the type in there for you. So we do not put these explicit types in there when Swift is able to infer them. Let's go back to rounded rectangle. Next thing I want to do is have it so that we can see our face up in real time and live action with the user by making it so that when we tap on one of these cards, it flips it over. Just like we have in our app over here. Every time we click on it, again, it's not going to be animated like we have over here because we're just getting started, but at least we'll be able to see the face down and the face up versions of our card really easily. How are we going to do that? Very simple. I told you that something that behaves like a view, like our card view does, or even like our content view does up there, it not only knows how to draw in its rectangle, but it knows how to receive multi-touch events and react to them. And we're actually going to spend pretty much an entire week talking about doing that. But the simplest way is a tap gesture. You can do that with a view modifier. So I'm going to add a view modifier to the Z stack. My Z stack represents an entire card. It's called on tap gesture, and it takes one argument, which is got the perform label here, and the argument is a function. Now this, again, surely you're not surprised to see functions as arguments at this point. But this function, it's not a view builder or anything. We're not making a list of views or a Lego bag here. Here we're just talking about just a regular function where we can do anything we want. And in fact, this function does not even return anything. It just lets you do any code that you want in here. And since this is the last argument and to this function, it's the only argument to it, we can remove this little keyword and remove the parentheses so this looks really nice and clean as well. What do we want to do when we tap on a card? Well, we want whatever face upness it has, face uppedness, to flip over, to be the opposite. So we essentially want to say is face up equals not is face up. We just want it to flip over. But unfortunately, you can see I'm getting errors here. Cannot assign to property. Self is immutable. It's basically saying I can't set this variable right here because self means my entire view, that's the code I'm in here, is immutable. And in fact, that is the case. All views in SwiftUI, every single one you see here, every one you're ever going to see, is immutable, cannot be modified. And you might say, well, how does my UI ever change then? Well, when things happen, for example, in your game logic or whatever, your entire UI is being constantly rebuilt. New views are being created to reflect the changes in your game logic and replacing old views. And of course, that's happening very efficiently. That's one of the great things about Swift UI is it allows for this entire rebuilding of your UI highly efficiently, but all the views are being replaced. There is no way to actually change this var, even though we call it a var. Once it's initialized either by the creator up here or by using this default value, it cannot be changed. All right, and that takes a little bit of getting your head around to understand that when our UI is changing, it's because all these views are being rebuilt, but that is the case. Now, we are not going to be working on the logic for our app until next week, and it is the logic that drives what the views are supposed to look like. But there is a small way that you can kind of create your own, you can think of it as like mini logic, but it's really just create a tiny little outside of the view storage space and have the view just look at that. And when that changes, the view will get rebuilt, but still pointing to that little piece of memory. And you do that by changing one of your vars to be @state. So putting @state in front of a var, a lot of people when they first are learning Swift UI, they think, oh, that makes this writable somehow, that now this view is mutable, it's got this variable is writable, but that's not true. This view is still immutable. It just turns this variable, instead of really being a Boolean, it's actually a pointer to some Boolean somewhere else, somewhere in memory, and that's where the value can change. But this pointer does not change. It's always pointing to that same little space over there. Now that might seem like a fine distinction, and it is somewhat of a fine distinction, but it's not really too much to worry about because we really don't use @state very much. It's pretty good at the beginning of the quarter when we don't have our game logic to drive our UI and we just want to do something like change our is face up around. But when we actually start building apps, we're not going to use @state very much. It's mostly just for temporary state. Things are like I'm in the middle of a drag or a pinch multi-touch and I want to keep some state as the drag's going on. And then when the drag's over, then I don't care about the state anymore because my logic will have changed presumably. Or you can use it just for state that only affects the way your view is displayed, not the logic of how your UI is playing a game or whatever. So we'll use this little @state. Notice that the error went away. Now we are able to do this is face up. If I click on cards, okay, we failed here, of course, because we introduced an error. So let's rebuild. All right, there we go. So now if I click on a card here, hopefully it should flip over, right? And click. Oh, wait a second. My preview here, when I click, it selects things, right? So, how am I going to check to see if my tap gesture works? Well, one way is I can run my simulator. So I'm going to go launch my iPhone 12 mini simulator here. Here are my cards, and I tap. Woohoo! It's flipping them over. Nice. Is face up, up and down. Very nice. So that's working. And this works here. We can rotate. Works over here. Very nice. Okay, so that's good. It's a little bit of a bummer, though, that anytime I want to test some multi-touch gestures, I have to go all the way back out to my simulator. I've been so used to doing it here in preview. Well, of course, we can do it in preview. All we need to do is use this little button right here. You see where it says Live Preview? If I click Live Preview, then it goes out of the mode where clicking on things selects things, and it still have pause and resume. So I'm going to resume here, and it's going to be showing me the latest UI, but now tapping in here is not going to select. It's going to do any multi-touch gestures like this one. Ready? Boom. You can switch back and forth really easily. Turn off live preview. You're back into clicking on things to select them, then back into live preview to make sure that your multi-touch gestures are working. So just to summarize here, when we are changing face up as a result of this tap gesture on the Z stack, we are actually changing it in memory somewhere, And our is face up is pointing to that. So whenever it changes, SwiftUI is smart enough to notice, oh, whoops, this thing is pointing at some is face up Boolean somewhere that changed. I need to rebuild this view, and it will recreate the body right here. And when it recreates the body, of course, the is face up will be different, and it'll choose whichever of these makes sense, right? Whichever of these if cases make sense. So that is the process by which this is happening. And this is a little miniature of the way SwiftUI works once we really have our game logic going. When the game logic changes, it notices which views are going to change as a result, and it rebuilds their body. So that's why it's rebuilding this all the time. These things are read-only, so if something changes, we have to rebuild this view, rebuild its body. So what else can we do here? Well, all of our cards, unfortunately, are airplane cards. It'd be really nice if we had our cards be something like this, where they were different vehicles than airplanes. So let's do that. How about, where is our airplane? Okay, airplane is right here. So this little string is in every single card view we ever create. That's why they're all airplanes. But what if we parameterize this? Just like we have this is face up var here, what if we create another var? We'll call it content because it's the content of our cards. It's just going to be a string. A string, by the way, very important struct inside of Swift. It is, obviously used in text and everything else. This is the kind of struct that you're going to want to become familiar with by looking in the documentation. And in fact, let's take a little brief look at how we can look in the documentation, because there's a quick way to get into the documentation from your code, which is to use Option key. Holding down Option, you see it turn to a question mark there, and click. When you do Option click, it's going to give you a little summary from the documentation about this type you clicked on, in this case, string. See, tell you just kind of a little bit about how it works. But you can also click Open in Developer Documentation. It'll bring up the documentation. Now you get a long description of everything that string can do. I told you it was an important struct. You can do a lot of things. And a list of every single function and var that it has and what they do, what the arguments are, how to call it, etc. Lots and lots and lots and lots of stuff in here. You can also search. If you go up to search up documentation up here, search for other things. And I try to make it so that you are going through this stuff as you learn this stuff. Asking you to go through the entire documentation and learn stuff would be a challenge, to say the least. It's very SwiftUI, obviously very expansive. But this is something you don't want to skimp on either. And when you get to important classes like string, and we're going to talk about array in a moment here, those are things where it's really good to read this introductory section right here. And, past that, you're going to be searching through here a lot to find functions and variables that you're looking for. But eventually you will become a master of all of this stuff in the documentation. You can also bring up the documentation, by the way, up here in the Xcode menus window. Developer documentation brings that same window up. All right, so if we have this content string, then we could just use this content right here. Content, and that would choose that content, whatever this var is, instead of the airplane. Now, just with face up, like with face up, this has to have a value. This can't be just set to nothing. And there's really no good default value here. We don't really want our cards to default to being airplanes. Well, this is the same errors we were seeing before with is face up. And we're going to fix it in exactly the same way by saying, all right, you've got this unset variable content. I'm going to set it for you. So let's set it and pick some vehicles here. Edit, emoji symbols. And we'll take train. That train is cool. Do a little bit of copy and paste to make this go quicker. All right, so we have now changed this content argument for each of our card views. And so when we resume, our cards look different. All 4 cards are different. And we're still in live preview, even though we resumed and we changed code, so we can still click. So that's really neat. We got different cards going on right here, but it's a little bit, we wouldn't really, probably never write our code like this, where these 4 emoji are kind of hardwired in here. We really would rather put these in an array or something like that, and then pick these out of an array. And eventually we'd like to have a for loop in here. But I think I mentioned earlier that these bags of Lego, while they can have local variables and ifs, they cannot have a for statement. So we're going to need a special bag of Lego making view that does for loops. And we'll see that in just a second. But before that, let's just put these four things in an array because we need to learn about array anyway. Array is a very important struct, just like string in Swift UI. So I'm going to put this up here, var, I'm going to call it my emojis, and I want it to be equal to an array of things. And in Swift, you can just put open square bracket, close square bracket, and a bunch of things listed in there, and you just created an array of something. So if I want to put these four emoji in there, it's as simple as that. Now, once again, notice I didn't specify the type down here. I let Swift figure it out for me automatically. But if we wanted to type this here, what type is it? It is an array, but just like in Java, you can't have an array that just an array of unspecified typed things. Swift is very strongly typed and it wants to know what type. So in angle brackets, you put what type is in the array. So this would be the type of our emojis var here. It's an array of string. Now, arrays are so common to create in Swift that there's a little bit of a shorthand for doing this, which is square bracket string. That's just another way of saying array of string. Exactly identical, not a different type. It's exactly the same as array with angle bracket string. But again, we don't need that. We'll just take that off. We'll let Swift infer it from what it sees here, which is that it's an array with strings inside. Now that we have this array right here, we could replace these here with emojis sub 0, for example, and then emojis 1. So arrays are indexed from the 0th element like most languages do. And we'd have to be very careful here. We wouldn't want to say emojis 4, oops, or 5. We want to stay within the bounds of it because if you access an array outside of its bounds, if you use an index here that's outside of its bounds, you will crash your app. Your app will raise an exception and crash. And kind of you want that because if you were outside of the bounds here, that's probably not good. You'd want to find that in your development process before you ship it out to your customers, right? So that's pretty cool. Get our emojis there. Let's make sure that still works. Resume. There it is. Works nicely. By the way, that option click that we did down here on a type, if you option click on a variable, like emojis, it will tell you the type. In this case, it says that it's an array of string. And of course, you can click here and go directly to the documentation as well. We're getting closer and closer to making this kind of a more extensible, expandable kind of UI for our cards. The next thing that I want to do here is do that for loop like thing that I was talking about in here. We can't use a for loop. We'll talk about what a for loop looks like in Swift later, but first we're just going to do this new bag of Lego thing that essentially is a bag of Lego that creates a view for everything in an array. That's exactly what we want here. We want to create a card view for each of the things in our array. This bag of Lego view that does that is called a for each, and it just takes the array that you want to create something for each, and then it has a content parameter, which is another bag of Lego. So it's going to essentially create this bag of Lego this many times, however many things are in here, and then this itself will become a bag of Lego. So since this is going to be a bag of Lego, lots of Lego here, it only makes sense to put a for each inside something like an HStack, a view combiner, because the for each itself is not a view combiner, it's just a bag of Lego maker. Right? It makes a bag of Lego filled with stuff by doing something for each of the things in this array. This content can just be our card view. So for each of the emojis in here, we're going to build a card view. So now we don't need these. And of course, we're not going to build the card view with the first thing in the array. We really want to build it for each emoji somehow. Somehow we're going to have to specify the emoji each time this for each goes through. And to do that, we're going to show you something new, which is that functions like this is the special view builder function, but it's still a function, can have arguments. None of the functions we've seen so far that we've used here has had any arguments. Some of them have returned things, obviously, but none of them have had arguments. So how do you put an argument to a function? Well, you just put the name of the argument and in. And there can be multiple arguments, of course, arg2, arg3. You can have as many arguments as you want. In this case, the for each only wants to pass one argument, which is the thing that it's currently working on as it goes through each of these. So this is going to be the emoji string. So it's going to be the train the first time through, and we're going to create a card view of a train. Then there's going to be a rocket ship the next time through. We're going to create a card view for the rocket. And those are all going to be put in this Lego bag that's being created by this for each. Very simple. Now, we still have an error here. It says referencing initializer for each requires that string, which is the things in the array right there, conform to identifiable. You're going to see this phrase conform to quite a bit in this class. And it's really the same as what I was saying when I said behaves like. So this content view behaves like a view. This card view behaves like a view. These things in this array, if you want to do a for each, they must behave like an identifiable. See this thing identifiable? What is an identifiable? It's a thing that has any kind of struct can be an identifiable, but it has to have a var called ID, which uniquely identifies it. Now, why does the for each want the things in this array to be uniquely identifiable? Because it's going to create a view for each of them. And if, for example, this array right here should be reordered or new things added to it or things removed from it, etc., it needs to know which things changed in the array and then adjust the views accordingly. So it needs to be able to uniquely identify everything in the array to match up the view that it's going to create for them. So it makes total sense. Of course, the things that we're doing for each, we have to be able to uniquely identify them. Now, unfortunately, a string has no such thing. If I had two trains here, there's no way to tell this train from this. They look exactly the same. Now, this is not going to be a problem when we build our real card game over here, because our for each is not going to be going for each through emojis. It's going to be going for each through cards. Our game obviously knows about some concept of a card, and we have to go through the cards because some cards can be the same. This checkered flag and this one, same emoji, but those are clearly different cards. Look, the timer is different on this one right here. And obviously I have to see if you've chosen these two cards and see if they match. So they have to be different. So it's not going to be a problem when we have the logic of our game. But in our little demo here where we're just making strings, it's a problem because there's no way to uniquely identify these strings. So we're going to work around that in our demo world here, just by picking a different string for every single card. All these cards, look at that, different vehicle. There's no two vehicles alike. And we're just going to have to live with that. And if we do that, then we can go back here to for each and tell the for each, yeah, just use the string itself as the unique identifier, even though it's not actually unique. Do it anyway. We do that with another argument to for each in addition to the emojis and the content here called ID, which tells it how to identify it. And it's kind of weird syntax here, which is we do \dot, and then we can put the name of a var here that string responds to, and that's what it's going to use as the identifier. String doesn't really have a var that's unique, as we know. So we're going to use a special var called self. All right, all structures have this var on themselves called self, which means the struct itself. So that's perfect for string. If I say dot self on a string, I get the string itself. So now this string is in fact the identifier that the emoji is going to use to identify them. Now, let's see what happens when we do that. We'll run it in our simulator first because we want to be able to flip these over here. There we go. We got our 5 cards. See, 2 trains and the other 3 things. That's what we have here, 2 trains and the other 3 emojis. And if I click them over, they're working great, working good. Yeah, the train, uh-oh. You see when I tap on the train, it's using the same view for both of these because, again, the for each can't tell these apart. So when it sees the train, it uses the card view it's already made for a train over there. And that's kind of weird behavior, and you really would just never want to do this, okay? You don't really want to have arrays that have non-identifiable things in them be passed to for each. So we're not going to do that. We're going to go back to having just the for. We're still in preview mode over here, so this is working fine over here as well. We can clean up our code a little bit here because, of course, content is a function, an argument that's a function, and it's the last one. So we can take that off of there, get rid of the parentheses. Now, the next thing we're going to do is put these little buttons on here. Add cards, remove cards. We want to be able to add and remove cards. And to add and remove cards, we can't have this fixed array that is always being entirely displayed right here, because we want to be able to vary the number of things that we're showing. So I'm actually going to do that by creating a much larger array, and then here only showing a subsection of the array, depending on how many of these cards we want to show. And just to make this typing go fast, I actually have a little code snippet that does 24 vehicles, but I'm only going to show the first, let's say, 6 of them. So how do I have an array, a big array like this, and then only show some of them? Well, we can index into the array, and instead of doing a single index like 5, which would just be one of them, I can actually do what's called a range. This syntax right here is a range. There's both this kind of range, which is 0 up to, but not including 6, or up to and including the number 6, which would be 7 items over. So here we're saying just pick the first 6 of these. So let's see if that works. Sure enough, we got 6. We can flip them over. Looking good. Should be able to do the same thing right here. Resume. Get 6. Excellent. Now, if we change this 6 to 4, now we're only getting 4. If we change it to 8, now we're getting 8. Our plus minus is essentially changing this number right here. Right? When we go over here and say more cards, please, or fewer cards, please, we are changing that number, that 4. So this just wants to be a variable. So let's make a variable for that. I'll call it my emoji count, and it's going to be an int. And we'll start it off at 6, let's say. Of course, we can have Swift infer that int, so we don't need that, because this is clearly an integer right here. If we said 6.0, by the way, it would infer it to be a double precision floating point number. So let's take this emoji count and make that be the max emoji count. And let's resume over here. We got 6. If we change this emoji count to 3, we'll go down to 3 cards. If we change it to 10, then we have 10 cards. So this is great. All the buttons we are going to add here have to do is change this emoji count bar. How do we add a button to our user interface? Before to make it a little cleaner here. How are we going to add a button? We want a button somewhere in our UI, which is add a card and remove a card. Well, adding buttons really easy. Of course, there is a Lego brick, which is a button, and we're going to put it right below our H-stack. So we've got our H-stack right here. I'm going to put this button right below it here that adds a card. And how do I stack this H-stack on top of something else? I'm going to use another view combiner, a V-stack. V-stack stacks this stack with a button. And what are the arguments to making a button? It has 2 arguments, basically the action, which is a function, and the label, which is also a function. it makes sense that the action would be a function similar to on tap gesture had a function right here. But what about label? Why is the label of a button a function? Well, the label is what appears when the user sees on screen to tap on. And usually this would be, for example, a text, like our text that might say add card, something like that. And you can see it's actually appearing down here in the UI. It's a function because it's a view builder. So it's a bag of Lego. You might be making more complicated types of content for your cards. For example, it might just be single text like this. What if I wanted it to be add with card on the second line? Well, it's perfectly allowable for me to make a VStack in here with text saying add and another text saying card. Here's my label. Here is the function, the view builder function that's returning the view. So this can be an arbitrarily complex view. Anything you want in here is perfectly fine. So there's add card. And maybe we have another button called remove card. We've got add card and remove card. And the action for each is obviously different. An action for an add card is emoji count plus equals 1. This is emoji count up here. And this button is emoji count minus equals 1. So we got our buttons here. It kind of looks okay. But we have a problem, same problem we had below with is face up. Left side of mutating operator isn't mutable, self is immutable. We know that these are immutable. So again, we'll just for demo purposes, put this off somewhere else and have emoji count. There should be a pointer to it, and that makes this work. And you might find in your homework that you might want this to end up being @state as well. A little hint there. This is nice, but I really don't want add card and remove card stacked on top of each other. I want them, you know, one on each side like this, minus and plus, the minus one on the left and the plus one on the right. So how do we do that? Again, just throw them in an H stack. That will stack these things horizontally, this here. And if I want the second one here, the remove card to be first, I can just pick it up and put it here. Now I've got my remove card and add card. Try again here. Got move card and add card. Again, not quite what I want. I want them more spaced out. There is another Lego brick that you're going to use, that you'll use all the time when laying out, called spacer. And a spacer is always going to grab as much space as it can. The remove card and the add card, they're going to be as small as they can just to fit their text, and the spacer will grab all the rest. But this has pushed these a little too far out to the edges. So can you think of how I might make these not go quite so far to the edges? How about if I take this H stack and add some padding horizontally? Move them in a little bit. Code is starting to get messy again. This is pretty long. I told you these views are supposed to be really, really short little views. And so we could turn this button here into a new struct, but it's a little bit overkill. When we created this card view struct, it made a lot of sense because first of all, it was more complicated. It had the Z stack with all this stuff in, whereas these buttons just have a single button. But second of all, it had all these bars and all these things to configure it, etc. And the buttons really don't have any of that. When you have something like this that's making the code really long and hard to understand, but you don't want to go so far as to make it its own dining room chair Lego, another solution you can do is to create a var for it. We could create a var, let's call it remove. It's some view. It's going to be this button. That's it. And yes, this is saying return, but since this is the only thing in this inside this function right here that sets the value of this, we don't have to say return right there. And same thing, we could create a var add for the add button. It's some view as well, and just put this button down in there. Now up here, we can say remove, and then spacer, and then add. And now this code is back to looking really clean, very understandable. And the last thing I want to do is change this add and remove to this nice icons here, these plus and minus icons, where do those come from? If I was writing my own app here, then maybe I would want some images for this and I'd hire my graphic designer to go and do them. But for standard things like give me more of these or give me less of these, things like that, it's really better if you use the same images that all other designers are using out there in the world. Because users get used to it. Oh yeah, plus in the circle, I know that, boom. They click on it with confidence because they've seen it in other apps. Apple has made hundreds and hundreds of these pre-built little symbols. And the challenge for you is just to pick the right one. And so they provided a really cool app for you to search around all these symbols by keyword and find the thing you want. Let's look at that first, and then we'll see how we actually create an imaged Lego brick that would show this. The app we want is called SF Symbols, and you get it by going and in your web browser and going to developer.com/sf-symbols. And when you go there, you're going to see this app. There it is, Symbols 2. You're just going to download it and then run it. And when you run it, it looks like this. It's essentially just a big search engine for all of these images. And you can see lots and lots of them. They're grouped by type, but you can also search. So like I might say, I want to add something. Now you're getting all the ones that make sense for adding. And you can see here's a plus with the circle. There's also a plus with the square. And it might be thinking which ones I want to do here, but I think plus with a circle is more appropriate to what I'm doing there. Plus.circle is the name of it, plus.circle. That's all you need to know is this name. And when you have this name, you can put it in your code. So let's go back to our code and add that. Instead of this add card VStack right here, two things piled on top of each other, we want a different kind of Lego brick, which is called an image. And when we create the image, there's actually a lot of ways to create images. Remember back here in our navigator, we looked at assets. If we drag JPEGs in here and give them names, we can use our image by name there. But if we want one of those SF symbols from that app that we just saw, we want to use system name as the argument or the label for the argument. And then you just do your plus.circle that you found when you looked it up. That is just using a different view for that. Resume here. We see we've got it plus right there. And we can do the same thing for the minus. Let's go back to SF symbols. Let's look for remove and see what we find. Here we go. We're looking for a similar kind of thing. Oh, there it is, minus.circle, it's called. So come back, minus.circle, image system name minus.circle. Couple of things not quite right here. It's getting close. First of all, these things seem very, very small. We're already using large title here for the text on our buttons. We can do the exact same thing and use large title for this H stack of these two buttons. So just like same thing, I'm padding it here. I'm also going to say use the font large title, and that's going to filter down inside this H stack into all of these buttons, and they've all of a sudden become larger. I could also put a spacer perhaps between this H stack at the top and these buttons down here below. I can even enforce some min length of that spacing. Maybe I want at least 20 points or something like that. But a lot of times you want standard default spacing because, again, it can be device dependent, different on an Apple Watch than it is on iOS. I know it's hard to believe, but these things that we're building, we can build them so that they would work on Apple Watch, or even if we're just building a very Apple Watch specific UI, we're using the same tools here. I think we've got this UI how we want it. Let's see if it's working. So I'm going to hit plus. Yeah, 5 cards. 6, 7. Oh yeah, lots and lots of cards. Minus. Oh yeah. One thing we weren't very smart about here was that what happens if we go minus, 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 minus? Oh, preview crashed. Why? Because I kept going minus so much that minus count went below 0. And then I tried to create this little range of stuff inside my array where this was negative. So that's clearly no good. So we really need to protect ourselves against those array index out of bounds. So here we'll say if emoji count is greater than 1, then we'll do emoji count minus 1. And here we'll say if emoji count is less than the emojis.count. Emojis.count, this is just a var in an array that says how many things are in that array. Now, when we're over here and we do minus, 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 it won't let us go more minus than that. And plus, 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 plus won't let us get to more than 24 of them over here. The last thing I want to do is make it so this code is a little cleaner. You can see that this button has 2 arguments. Both of them are functions. So you can do the thing where you get rid of these keywords and do this outside, even if you have 2 at the end. And you just do it by putting the label of the second one right after the first one. Here I've got this one, then just this label, and then this one. We keep the label for the second one if we're using the last 2, but we still don't have any commas or space or parentheses or any of that. Get rid of the comma in there and all that. So we've got a little bit more to do to turn this into a grid. But before we do that, I'm going to take 5 minutes and just review everything we've learned so far. We learned to build user interfaces with SwiftUI by building these data structures that behaved like a view. And this idea of building a structure that behaves like something is the fundamental underpinning of the functional programming methodology in Swift. Now we learned that Swift also does object-oriented programming methodology, and that we're going to combine those 2 methodologies next week when we add logic to our application, but that the UI portion is all functional programming. We learned that a view is a rectangular area on screen. It can draw, it can receive multi-touch events, and we learned that just saying that we behave like a view gives us enormous power. For example, we can set fonts in our cells or set our padding or even handle a tap gesture just by calling a function on a view. But even more importantly, we learned that we could put views together to build complicated user interfaces. And we get all that mechanism just by saying we behave like a view. But with that great power comes a little bit of responsibility, which is that we have to implement this one variable in our data structure called body. And this body's type is some other view. So the body of our view is some other view. And this might have been initially perplexing, but it made sense once we started talking about views like Legos, where we're going to piece them together to build more powerful Lego, like a dining room chair Lego, and then piece that together with other more powerful Legos to make a dining room Lego, and then a house Lego, and the neighborhood Lego, the universe Lego. And once we had this model, it all made sense that the body of a given view is some other view. Now the value of this variable is calculated by executing this function, which just gets dropped right in the middle of our code. And we found that dropping functions in the middle of the code is something we do all over the place in Swift. We did it a dozen times in building this user interface. And so it became commonplace for us to do it. Now this function obviously has to return something that is a view, and we know that the compiler is going to replace some view right here with whatever the actual view that's returned from here is. This view that we're building in here, we make it somewhat out of individual Lego bricks, like spacers, and also images, and also text down here. But largely we make them out of these view combiners, or Lego combiners we call them. These Lego combiners, they are created like Lego bricks. They might even have arguments, alignment or spacing or whatever, but they all are going to also have this argument, which is another function that's dropped in there, which is a list of the views for it to combine. And that list of views we call a bag of Lego view, and it's made with kind of a special functional syntax called view builder. So these are view builders. They allow us to just list our views, right? 1, 2, 3 views right here, or down here we've got these 3 views listed. We noted that we can also do if-thens to determine which views get into our bag of Lego, and we can even do local variables to clean up our code as well. Along the way, we learned another way of doing bag of Lego, which is for eaches. For each creates a view for each of the things in an array. This array, or in our case, a little subpart of an array, has to contain things that are identifiable so that the for each can keep track of which things in the array match with which of the views it is creating. It normally does this by requiring the things in the array to behave like an identifiable. Just like we say our structure behaves like a view, we could say that the things in this array behave like an identifiable. And all it means to behave like an identifiable is that you can identify it, uniquely identify that thing in the array from all other things in the array. Well, we're putting strings in here. Unfortunately, strings do not behave like an identifiable because 2 strings that look exactly the same might be different strings. So we kind of cheesed it with this little argument right here that forces the for each to think that each of the strings was itself identifiable. And then we made sure to never put the same string in our array twice. So that was a bit of a cheese. When we do our actual app, we'll be putting cards in these arrays. We'll be for eaching through cards, not emoji. And the cards will, of course, have to have some sort of unique identifiability. And that's something we will cover when we do our cards next week as part of our logic. Now, we learned, of course, that these view combiners, when we gave them a bag of Lego, that the Lego that was inside their bag of Lego could be more view combiners that have their own bag of Lego. And those bag of Legos could have more bag of Legos inside of them. This allowed us to build pretty complicated user interfaces. But our code started to get a little bit long, and we know that the design methodology of Swift UI is that we want our views to be really small, not a ton of code. So we started factoring out some of the code. One way we did that is by creating a dining room chair Lego, creating our own struct that behaved like a view that represented a little piece of UI, in this case, one of these cards. And when we did that, we learned that these little dining room chair Legos could have variables that would configure how they look, whether it's face up or face down, what sort of emoji is on the card. And finally, we learned that we could also factor out some code just by creating our own little vars, that this body var up here was not the only view that we could create. We could create our own sum views, for example, to add a button and put that inside with just referring to the var. And this cleaned up our code quite a bit. And that's all there is. Next week, we're going to be adding logic, and in the weeks after, we'll be adding things like animation. But all of those things are all going to be within the framework of building UIs in this way. There's really not a lot more to it. There's a few more view combiners for us to learn. There's a few more of these Lego bricks for us to learn. And of course, there's a lot of view modifiers for us to learn. But for the most part, you've already learned the fundamentals of building Swift UI apps. Okay, the last thing we want to do this week is put our cards into a grid instead of all horizontally like this. We want them to like this. We also want them to look more like cards, not these tall, skinny things. Before we go off and do that, though, I want to address one other issue here, which is these buttons down here. See, these ones are blue, and the ones over here are red. So why are these blue and these red? Well, this blue is kind of standard control blue in the UI. And we really want these buttons right here to be blue because when users see this blue, they think, oh, I can probably touch on that. This red, it's pretty obvious, but they might not be 100% confident that they can click on it. And then we'll go do the grid. So let's jump back and do that. The red is actually very easy to understand why these buttons are red. It's because this foreground color red is being applied to the entire VStack of our UI, including the buttons. Fixing this so that only the cards are red is a simple matter of taking this foreground color out of here and putting it on this H stack that has our cards so that it's only affecting this H stack. Sure enough, now the cards are red and this has reverted to its proper default standard control blue. Now that we fix that, how do we make this H stack here into a grid? This is very straightforward. We're just going to replace this H stack with a new view combiner called a lazy V grid. We'll talk about why it has the word lazy in its name in a few minutes. A lazy V grid basically lets you specify a number of columns, and it's going to make that many columns here, and then it'll make as many rows as necessary. And yes, there's a lazy H grid where you specify the rows here, the number of rows, and it'll make as many columns as necessary. So this is really great. Unfortunately, you can't specify the number of columns just by putting the number here, like 3 columns. Instead, you put an array of grid items. So however many grid items you put here, there's 1 grid item, here's 2 grid items, here's 3 grid items. See, the more grid items I put here, that's how many columns it makes. Why does it do grid items here as opposed to just the number 3 that I want 3 columns? Well, because these grid items let you control the columns more. This lazy V grid, of course, more powerful than just give me 3 columns and I'll do it for you. For example, I could put in here grid item fixed at 200 wide. And so now this first column is fixed at 200 wide. The other ones are just fitting in whatever space is left over. And that's because the default in here is actually something called flexible. These are flexible grid items, and so they'll flex to whatever space is available. But we're going to go back to just normal 3 columns that are the same. And we're going to try and understand what's going on with our UI here because the cards have changed shape. They're kind of these short little guys. They're wide, but they're short. They don't really look like cards much anymore, although they didn't look much like cards when they were in H-stack either. They were really tall, way too tall for being cards. And why is the lazy V grid doing this? Why is it making them this size? Well, the H stack, it uses all the space it can. Whatever space it can get a hold of, it uses it, and it uses it in both directions, height and width. That's why we got tall cards that were as tall as they could be and as wide as they would fit. So that is the H stack's way that it distributes its space. A lazy V grid has a different strategy. It uses all the width horizontally for its columns, depending, on the fixed and flexible in here. It's using all that space. But vertically, it's going to make the cards as small as possible so it can fit as many as possible. So that, for example, if we go to emoji count 24 right here and resume, all 24 cards are going to fit in this lazy V grid, which is great for the lazy V grid. It's not exactly what we want in terms of the looks of our card, but you can see why lazy V grid is taking this strategy. And there's another thing to consider when it comes to these different strategies between lazy V grid and the H stack, which is this spacer right here. When we had an H stack here instead of a lazy V grid, the H stack was using all this space, so our spacer just ended up being this tiny little sliver of space between our buttons at the bottom. Here, I'll make it so we can select them. Our buttons at the bottom here and the H stack that was at the top. But now that we've used a lazy V grid here, it doesn't use all its vertical space, and so the spacer has taken up all the space in between. And that's the way spacers work. They take any open space that's available that no one else wants. So these buttons didn't need any more space. The lazy V grid, this is all the space it needed, so there was extra space, and the spacer took it up. If I take the spacer out of here, I get a very different looking UI because now these two things combine to make this V stack. This is the V stack on the outside here. And this V stack no longer needs the whole space. So it just centers what's in there. So that's why we see this V stack centered instead of using the whole space. When I put the spacer back, now there's somebody to absorb extra space. And so the V stack will be as large as possible. So this is different kind of spacing here than using padding, which is fixed, and also using spacing as an argument to your VStack here. That's also fixed spacing. This is flexible spacing that absorbs any extra available space, and that causes other views like these and these to pin to the edges. Just want to make sure you understand the difference between using spacers here and just using padding or spacing. Okay, let's get back to making our cards look more like cards. What makes a card look good when it's like this? Well, it's kind of too wide for every 3 high. Its aspect ratio is kind of 2 to 3 approximately. And I want my cards to look like that, 2 wide, 3 high. If you look at most cards, playing cards, all these, they're generally about 2 to 3 in aspect ratio. Well, this shows a little bit of the power of SwiftUI, how easy it is to make these cards be 2 wide, 3 high. And that is with a view modifier called aspect ratio. I'm just going to 2/3. It has another little argument here called content mode. I'm going to do fit. Won't really talk too much about that. It's fit versus fill. That's just how it arranges the space that it's given. But you can see that this has immediately made all of these cards be 2 wide by 3 high in aspect ratio, still using all the width available to the number of columns that we have right here, but it's making the height match to be 2, 3. So if I made a lot more columns here, let's say we made 6 columns, so I'm going to copy this and paste a whole bunch more, then again, they're still 2 wide to 3 high, but they're making fit 6 columns right there. The problem when we only had 3 columns, the cards were nice size actually, maybe a little too big, nice size, but they didn't fit on the screen. In fact, they pushed our plus minus buttons completely off the screen. If we go back into preview mode, you can see I can't even, I got too many here, but let's go back to 4 and that doesn't even fix the problem because watch. I have 4 cards, great. I'm going to add some more cards, add another card. Now my minus button is gone. So clearly this is not good. This view is expanding to fit and now it's smashing into these other views. So what do we do when we have a really big view like this that can expand and smash into other things? Well, we can put it in a scroll view. And a scroll view is just another view, kind of like HStack or Lazy V-Grid that contains other views. So I just say scroll view, this in here, scroll view like that. Let's put this aspect ratio on another line so it's clearer. And now I have these 4 cards and they're in a scroll view, you see? So now if I hit plus, 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 it actually added the card down there. You see? Plus another card. And now we can remove and add as many cards as we want. I'm going to take a second now to explain this word lazy in our Lazy V-Grid. So a Lazy V-Grid is lazy about accessing the body vars of all of its views. We only get the value of a body var in a Lazy V-Grid for views that actually appear on screen, that scroll on screen. So this Lazy V-Grid could scale to having thousands of cards because in general, creating views is really lightweight. Usually a view is just a few vars like is face up and content in our card view. But accessing a view's body is another story. That's going to create a whole bunch of other views and potentially cause some of their body vars to get accessed. So there's a lot of infrastructure in SwiftUI to only access a view's body var when absolutely necessary. This laziness we see in Lazy V-Grid, that's only a minor example of that. We'll learn a lot more next week about how and when the system accesses a view's body var. This is looking really great. This is exactly what we want. Our cards are too big, so we can scroll around on them. But I actually notice a small problem here, which is that our card is actually getting slightly cut off. This scroll view cuts off anything that doesn't fit in the scrollable area, and it's cutting the edges of our card off. Now, with the resolution of the screen you're looking on, you probably can't see that, so let's go down and make our line width much larger, about 8. Now hopefully you can see that it's cutting off. You'll make it even larger, say 12. And why is it cutting off this edge? Well, it has to do with how stroke works. Stroke draws a fat line, however fat you say there, 12 points in our case, draws this fat line around right on top of the border. So some of the line is spilling on the inside of the shape and some is spilling on the outside. That's not actually what we want here. We want this entire border inside the boundaries of the shape. And there's a great function that does exactly that called stroke border. Okay, so this is a modifier that strokes just like stroke does, but it strokes the border, so stroking on the inside. Exactly what we want. So now we can go back to our 3. Cards are looking good. They're not being cut off there. Let's go take a look and see what it looks like in light mode on our simulator. Make sure everything is working over there. And appears to be. Can add more cards. Scroll around. How about landscape mode? Yes, there it is. There's all of our cards. Now it's working here in landscape, but it doesn't look very good. These cards are way too big. And if you look at this simulator over here, when I go to landscape mode, it showed more cards. But it's showing 8 across right there and only 4 in portrait. Whereas here we're showing 3 no matter what we're in, portrait or landscape. So how the heck did I get this version of the app to show more cards in landscape than in portrait? Well, there's a little trick we can do with Lazy V Grid that tells it to please plug as many things as you can fit across before you go to the next row. And here's how we do that. Instead of having 3 grid items where there's a fixed 3 columns right here, I'm actually going to have just 1 grid item. Now, this 1 grid item that I have is going to have a little special configuration so that instead of putting 1 card per row, so there's just 1 card, 1 column, 1 row, instead, we're going to ask the Lazy V Grid to take all these cards and pour them into this 1 column as much as will fit, then it can go to the next row. So it's kind of an odd way of describing what's going on, but we're really having 1 column, and that 1 column contains multiple items, and it just pours them in there. And it pours them in there sort of like text in a book, where the things that it's pouring in are like words, and it just puts the words on, it gets to the end of the row, goes to the next one, puts more on, keeps going down to the next one. And it also right justifies the text so that it picks the width that exactly fits like it was doing before. So how do we get our Lazy V Grid to do this? Well, we're going to take this 1 grid item right here, and instead of saying dot fixed or dot flexible, we're going to say dot adaptive. Now, when it pours these card views in there, Lazy V Grid is going to want to put as many of those cards in there as it can in each row. So we need to let it know the minimum width we're willing to accept for each of our card views. So we do that by just saying minimum. And let's pick something like 25, let's say. Oh, okay, so it took our 4 cards and poured them in there and made them as small as possible, but not smaller than 25. But 25 is clearly too small. Let's put more cards in there and see what happens. Go to 20 cards and resume. There we go, put 10 per row. Essentially wrapping again like text in a book, but that 25 is too small. Let's see what happens if we go to 100 as the minimum width. Well, at 100, we're back to 3 cards in each row, and obviously our cards aren't fitting. We're having to do the scroll view, so that's a little too big. Let's try something bigger, 65 maybe. 65 looks pretty good. That's 20 cards at least. Fits nicely. If we went to 24, we'd be back to scrolling, but that's certainly better. What about landscape mode? Let's go back to our simulator over here and rotate this thing into landscape. Woo! Look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it puts 9 across. So we get 9, 18, 20. Just got our scroll view here, luckily, because it's hard to pick a width that works well in both portrait and landscape. What we really want to do is pick our width based on how much screen real estate is being offered to us. We'll learn how to do that later, next week or the week after. But for now, we'll stick with 65 and we'll just rely on our scroll view here if we have to in landscape or if there's too many cards. Okay, that is it for this week. Next week, we will dive into the game logic for our Memrise game. See you then.
For more, please visit us at stanford.edu.